How do you solve complicated direct current circuits that contain resistors, capacitors, maybe even a combination of resistors and capacitors? Is it just Ohm's law that we need to know? Do we need to know Kirchhoff's laws? Is it just enough knowing them? Or do we need to really know how to apply these concepts depending on how the circuits are connected? Whether it's in parallel or whether it's in series, how are they connected? How do we apply all this? This is what I'm trying to show you with these 10 examples of different direct current circuits. So let's get into it. Here's the first question. Say it's a car battery with a 12 volt EMF and an internal resistance of 0.050 ohm is being charged with a current of 60 ampere. So a car battery, which is rechargeable, is now being charged. The battery has an internal resistance which is really small, 0.050 ohm, and the charging current is big, it's 60 ampere. Note that in this process, the battery is being charged. Yes, of course. A, what is the potential difference across its terminals? B, at what rate is thermal energy being dissipated in the battery? C, at what rate is electric energy being converted into chemical energy? So first of all, you got to find the potential difference across its terminals. All right, so here is the circuit that shows the battery being charged here and the 60 ampere current that flows through that battery, reversing the chemical process. Here's the battery charger. And when you apply Ohm's law, we know that the potential difference across its terminals, V is equal to E minus I times R. That's in the normal case. That's not the case when a battery is being charged. That is when you're using a battery, the terminal voltage is its EMF minus the current produced by it multiplied by the internal resistance. But in this case, because the battery is being charged, we got to change the negative into a positive. Because on top of the electromotive force E, we are also producing this potential difference. So to get the total voltage, you got to add them both. Or in this case, the EMF is 12 volt, the current is 60 ampere, and the internal resistance is 0.050 ohms. So when we multiply that and do the calculation, you get 15 volt. So that is the potential difference across its terminals, 15 volt. Next, at what rate is energy, thermal energy, being dissipated in the battery? Heat produced or thermal energy per second is I squared R. I squared R, heat produced per second. That's exactly what you're asked to find. At what rate means what's the heat produced in 1 second? So we just need to use I squared times R to get the heat produced in 1 second. Do we know the current? Yes, we do. It's 60 ampere. So that's 60 squared times the resistance. The internal resistance in this case is 0.050. So when you do that, we get 180 joules per second, which is also 180 watts. Next, at what rate is electric energy being converted into chemical energy? So remember that the heat that is produced is what is actually lost. So 180 joules is lost in 1 second. So we're not getting that. So what are we actually getting? Power in a circuit is the product of voltage and current. We know the voltage is 12. We know the current is 60. When you multiply those two, you're going to get 720 watts, 720 joules per second. And then we know that the total power I called it P sub T to show that's the total power. Although that's the total power, remember that we're losing 180 joules per second, so we got to subtract that to get 540 joules per second as the actual energy, electrical energy, being converted into chemical energy. That again shows that the smaller the internal resistance of the battery, the more electrical energy you can convert into chemical energy. All right. Here's the next one. What is the internal resistance of a voltage source if its terminal potential drops by 2 volt when the current supplied increases by 5 ampere? So we got to find the internal resistance of a battery, which is the voltage source, and the terminal potential is not given. What is given is the decrease in the terminal potential when the current increases by a certain amount. So we cannot use the formula directly, but we can start with it. We know that the terminal voltage is E minus I times the internal resistance. We know that. And so the change would be minus delta I times R. Why? Because E is a constant. E is the EMF of the battery that doesn't change. So now we can use that. We know that the change in voltage is 2. And I have neglected the negative sign because one is an increase, the other is a decrease, if you notice. So the negative goes off. And so you get 2 is equal to 5 times R because 5 ampere is the current. And then we can find the internal resistance easily as 0.400 ohm. The next part of this question is, can the EMF of the voltage source be found with the information supplied? No, that's impossible. Because when you have 2 variables, you can't just find that without being given the value. We need at least 2 equations. If there are 2 unknowns, we need at least 2 equations. And here we are only able to get 1 equation, so we cannot find the EMF of the voltage source. Okay, now let's move on because, like I said, we need 2 equations to solve 2 unknown quantities. So that is why we cannot do this problem. Here is the third one. Your cars, this is an important question, and this was asked on an exam, and many students found it very difficult. That's the reason why I've included it here. Your car's 30-watt headlight and a 2.40 kilowatt starter are ordinarily connected in parallel in a 12-volt system. That's how they are connected. So you have 2 things. You have a 30-watt headlight and you have a 2.4 kilowatt starter, both connected in parallel to this 12-volt car battery system. The question is, what power would one headlight and the starter consume if connected in series to the same 12-volt battery? So you got 2 connections. First, they are in parallel. And then you're asked to find what's the total power if they were connected in series. So from what's given in parallel, we know that the voltages in parallel are equal. So both the headlight and the starter would get 12 volt when in parallel. From that, we should be able to calculate the resistance of each one. So let's find the resistance of the headlight and the resistance of the starter. This is the formula. P is equal to V squared R. V squared by R, I mean. P is equal to V squared by R. So rearrange that and we can make R the subject. R is V squared by P. And the voltage is given as 12. So 12 squared divided by the power. So 12 squared divided by 30 will give us the resistance of the headlight, 4.8 ohm. That's R sub H for headlight. Similarly, we can find the resistance of the starter, which is again 12 squared divided by 2.40 kilowatt is 2400 watts. So you get 0.06 ohms. So now when you connect both of these in series, their resistances add up. Because when resistances are connected in series, you simply add them up to get the total resistance. So that's what I'm doing. Total resistance now is the sum of these two. And that's going to give, that's 4.8 plus 0.06 is going to give 4.86 ohms. 4.86 ohms. Okay, so that's the total resistance in series. What are we looking for? We're trying to find the power. And when components are connected in series, we know that the current flowing through them are equal. So if we can find that current, then we can use I squared times R to find the total power. So P is I squared times the total resistance, which, well, I have substituted for I as V by R. Current is voltage by resistance. And then that simplifies to V squared by R. And one of the 4.86 gets cancelled with the square, and we calculate that to be 29.6 watts. So in total, we only get 29.6 watts if they were connected in parallel. I hope you understand that. Let's move on to the next one. Number 4 is an electrical circuit that's given here. Consider the circuit shown. Find the voltage across each resistor. And what is the power supplied to the circuit and the power dissipated or consumed by the circuit. Okay. So what kind of circuit is this? All of the components are connected in series. We can see that. We have 1, 2, 3, 4, 5 resistors, and 2 batteries. 12 volt and 24 volt, and we have to find the voltage across each resistor. To find the voltage, you need to find the current, because we know in a series circuit the current is the same. Okay, so let's find the current. Since all the resistors are connected in series, you simply add them up to get the total resistance, which is 60 kilo ohms. And then because of the way the batteries are connected, if you notice, you see that the positive here of the battery is connected to the positive of the other one, which means they are opposing each other, because this is trying to send a current this way through the circuit, while this one is trying to send the current exactly in the opposite direction. So they're kind of opposing each other. In practice, batteries are never connected like that, because you don't want them to be opposing each other. But in this case, yes, it is. Therefore, the effective voltage is 24 minus 12, because they are opposing each other. If they hadn't been put in the other way, like if you had rotated one of the batteries, it would have been V2 plus V1. Remember that. In this case, it's minus, so it's 12 volt. And then to find the current, just go Vt by RT, which gives 0.2 milliampere. Once you get the current, to find the voltage across each component, just multiply that current with its resistance. Okay. So current times each resistance. Remember, it's in milliampere and kilo ohms, so they cancel out, milliampere and kilo ohm. So you're going to end up with volt. Just keep that in mind. So doing that for all components, all resistors, in this case, we get these values. Okay, so those are the voltages that we get. That should be easy to understand. And then we are asked to find the power dissipated or consumed by the circuit. Power used by the circuit. So the power coming in is I times V2, which is 24 times 0.2, and you get 4.8 milliwatts. That is the power coming in, because it's a 24-volt battery that's actually doing the work, And then the power out is IV1, because the 12-volt battery is also consuming. So that's why to calculate the power out, we're using that power across that battery plus I squared times the total resistance. So when you do that, you get 4.8 milliwatts. Oh, so the power in is equal to the power out in this case. All right, here is the next one. This is a circuit where we have to find the currents. And to find the currents in the circuit, we will have to use Kirchhoff's laws. Remember, there are two Kirchhoff's laws. One is the junction rule, and the other is the loop rule. In the junction rule, the total current flowing through any junction is zero. What does that mean? The currents coming in is equal to the currents going out. So that's for example, if you look at this circuit, you see at this junction, you can see that I1 is coming in, I2 is also coming in. So I1 plus I2 should be equal to I3. That's it. That is Kirchhoff's junction rule. Now, the loop rule. In the loop rule, if you move around the loop in the direction of the current, then you're going to take a negative voltage drop. If you go against the current, it's going to be positive. Let me just show you that in this loop. Let's look at this loop here. And imagine we are moving clockwise. So if you're moving clockwise starting from here, you're going with I3, you're flowing in the same direction as I3. So when you come here, since you're moving to the positive, you will go plus 21. But here you're going to go minus, what's the current through this? The current through this is I3. Yeah. So minus I3 times 5. Again, why is it minus? Because I3 is flowing this way, and we are also moving in the same direction. So it's minus 5 I3. When you come here, what's the current flowing through this? Oh, that's I2. Since we are moving in the same direction as I2, again it's going to be minus 6 I2 is equal to 0. So that's in the loop. So that's the loop rule. So these are the two rules we're going to use to find the currents. Shall we do that? Okay, so we'll have to apply at least the junction rule and then the loop rule in two loops. Okay, so we're going to go clockwise. And in this loop, it's V1 minus 2 times 12 plus I2 times 6 is 0. Let me explain that, because we're moving to the positive. So it's V1, and we're going in the direction of the current, and the current is 2. So it's minus 2 times 12. And then you're coming against that current I2, so it's plus 6 I2 is equal to 0. Okay, so that simplifies to V1 minus 24 plus 6 I2 is equal to 0. Now let's take this loop. In this loop, since you're going this way, it's 21, that's plus 21, minus 5 I3, minus 6 I2 is equal to 0. I already explained that. Okay. So maybe you want me to explain that again. It's 21, okay, since we're going down with the current, 21 plus 21 minus 5 I3 minus 6 I2 is equal to 0. So if you're moving the same direction as the current, it's negative of the product of the current and the resistance. Negative the product of the current and that resistance. You just got to be careful. So we get those two equations, and then when we apply the junction rule here, as I already explained, you get I1 plus I2 is equal to I3. So we just need to solve these three equations to find the currents. And we can do that anyways, but this is what I do. For I3, I am substituting I1 plus I2. Right here, instead of this I3, I'm substituting I1 plus I2. Distribute that. And so that makes it this equation. Now we have that equation with I1 and I2. Right. I1 is given, so I've just substituted the value of I1 as 2, which helps us to calculate the value of I2. All right, when you do that carefully, you get I2 as 1 ampere, which is a good thing. Once you get the value of I2, substitute it into that equation and find V1. So V1 minus 24 plus 6 is 0, which gives V1 is 18 volt. Remember that if you feel this is too fast, you can always pause the video. Okay? So once you get that, you can get the value of I3 as 3 ampere. So we got the values of I1, I2, and I3 simply by applying Kirchhoff's junction rule and the loop rule. Shall we move on? We have another circuit here. Consider the circuit shown below. Find I1, I2, I3, I4, and I5. Oh, so now there are 5 currents to be calculated. And find the power supplied by the voltage sources. Also find the power dissipated by the resistors. So now we have at least 3 loops. And we have to find all these currents. Once again, it's an application of Kirchhoff's rules, okay, the junction rule and the loop rule. So if you look at this junction, you can see that I1 and I3 are coming in. I2 is going out. So I1 plus I3 should be equal to I2. But if you look at this junction, then you see that I5 is flowing out, I3 is also flowing out, but I4 is coming in. Therefore, I4 should be equal to I5 plus I3, isn't it? That's what you get when you apply the junction rule. And then we can apply the loop rule in the circuits, and this is a loop that's quite simple because you only have one battery and a resistor. So if you apply the loop rule here, what are you going to get? You're going to get 5, because you're going positive, 5, and then minus 2 times I4 is equal to 0. So if you do that, you already get I4, and then we can get the other current. So let's do that. Okay. So I1 plus I3 is I2. And I4 is equal to I3 plus I5. Yeah, applying the junction rules at these 2 junctions. Then here is the loop rule applied here. No, so that's the loop rule applied here in this loop, right? Isn't it? It's 12 minus 4 I1 minus 3 I2 is equal to 0. That's right. And then in this loop, that will be 5 minus 2I4 is 0. So from there you get I4, and I4 is 2.5 ampere. Once you get I4, all right, now I'm using this loop. I'm applying it in this loop. So that would give minus 2I4 minus 2I3 plus 4I1. You know why plus? Because we're going against the current. Is equal to 0. And then I am substituting for I3 as I2 minus I1, because I3 is going to be I2 minus I1. I'm trying to get an equation with two variables, I1 and I2. Distribute that. It's minus 2I2 plus 2I1. And then you have 4I1. So that will be 6I1, right? Minus 5 minus 2I2 plus 6I1 is equal to 0. Yep. So I'm writing that equation down here and then just rearranging it just to make the I1s and the I2s come together. So now we have two equations with two unknown variables, and I'm going to solve them by multiplying the top equation with 2, the bottom equation with -3, and adding them. What's the idea? The idea is that -3 times 2 becomes -6I2, and here when you multiply you get positive 6I2. So on top you get -6I2, bottom you get positive 6I2, and you add them, they cancel out. So you get rid of I2, you're going to get the value of I1. But remember that this 12 has to be multiplied with 2, so that's 24. And then this is plus 15. 24 plus 15 is 39. And then here you have -8I1 and -18I1. So that's -26I1. All right, so rearrange that and you get I1 is equal to 1.5 ampere. Once you get the value of I1, plug it into this, and you're going to get the value of I2. All right, so 6 times 1.5 is 9, and then you get I2 as 2 ampere. All right, once you get I1 and I2, surely you can find I3 using this. I3 is I2 minus I1. So 2 minus 1.5 gives 0.5 ampere. And since we have I3 and we also have I4, now you can find the value of I5. See, Kirchhoff's laws are really very useful. And it's just one of the many network theorems that can be applied in DC circuits to find the currents and the voltages. Okay. So I hope with these two examples, you are well versed in doing problems by applying Kirchhoff's laws. Let's hope so. Let's move on to the next one. All right, here's the one. A heart pacemaker fires 72 times a minute. Each time a 25.0 nanofarad capacitor is charged by a battery in series with a resistor, and it's charged to 0.632 of its full voltage. What's the value of the resistance? So this is an RC circuit, a resistance, capacitance connected in series. Remember that a capacitance is always charged or a load to discharge only through a resistance. And most of the time that resistance is big. You cannot connect a capacitor to a battery directly and try to charge it because it'll be an instantaneous charging and the capacitor will be blown out. The dielectric will break down. So that's why a capacitor is always charged and a load to discharge by connecting it in series with a high resistance. That's exactly what's done with this pacemaker. So what's given? The value of the capacitance is given. It's nanofarad. And it says that it charges to 0.632 of its full voltage. But how much time? Oh, 72 times a minute. So we know that the time taken is 72 firings in 60 seconds, right? Therefore, what's the time taken for one firing? 60 divided by 72. So we have the time there. And this is the formula that we use to calculate the voltage. So V is the voltage. This is the maximum. And what's given in this problem is the ratio of the voltage to the maximum, which is 0.632. because this is the voltage at any instant t seconds, and this is the maximum. So we know this ratio is 0.632. We know the time, and we know the capacitance. We can easily find the resistance. Let's do it. Okay, when T is equal to CR is when V by Vm becomes 0.632. Okay, that's a very important point. You know, time constant of a CR circuit, time constant, is the product of capacitance and resistance. And it is defined as that time taken for the voltage to increase to 0.632 of the maximum. So from the problem, we know what's given as the time constant. So that's the quicker way of doing it. And we also know, since it's firing 72 times in 60 seconds, time taken for one firing is 60 by 72, which must be equal to C times R. There goes the problem. And now rearrange to make R the subject. Remember that the capacitance is 25 nanofarad, which is times 10 to the negative 9. And then calculate to get 33.3 times 10 to the 7 ohms. 333 mega ohms. Do you see how big the resistance is? That's usually the deal. The resistances used with the capacitance are usually very high. All right, we have 3 more problems to be done. Here's the first of the 3. If you wish to take a picture of a bullet traveling at 500 meters per second, then a very brief flash of light produced by an RC discharge through a flash tube can limit blurring. Okay, it's talking about using a flash with a camera, and the discharge needs to be really fast. That's what it's talking. Assuming that 1 millimeter of motion during 1 RC constant is acceptable, 1 millimeter of motion, that's all that is allowed during the discharge. And given that the flash is driven by a 600 microfarad capacitor, what's the resistance in the flash tube? Okay, again, it's a resistance capacitance circuit which is discharging. In this case, it's not charging, it's discharging, and to produce the flash. And the speed of the bullet is 500 meters per second, but the flash should be of a timing of the time taken for it to move just 1 millimeter. Wow, that's going to be a small time. So now the thing is, if it moves 500 meters per second, how much time does it take to move through 1 millimeter? That's the time in this. And then the value of the capacitor is given, okay? So 500 meters per second. So the time taken is the time taken to move 1 millimeter. Right. Which is 10 to the negative 3 meters. So we got to have both in meters. 1 millimeter is 10 to the negative 3 meters. So 10 to the negative 3 by 500. Small time for sure. 2 times 10 to the minus 6 seconds. So that's the time, but we know that the time is equal to the product of resistance and capacitance. So now that we have the time and we have the capacitance, isn't it easy to find the value of the resistance? It is. All right, so just divide 2 times 10 to the negative 6 by 600 micro. Micro is 10 to the positive 6. And so therefore, we get 3.33 times 10 to the negative 3 ohms. All right. So that's the first. Hope that's clear. Here's the next one. Consider the circuit shown below. What's the energy stored in each capacitor after the switch has been closed for a very long time? So first of all, you take a look at the circuit and you see, okay, there is a switch here, which it says has been closed for a long time. And you have resistances, 3 of them, and you have 2 capacitances, two of them. So when the switch is closed, the capacitors will get charged. But if you remember, the charging rate is initially very high and then it slows down. So if the switch is closed for a long time, then the capacitors get maximum charged. When the capacitors get maximum charged, there is no current flowing through the circuit. That's the most important thing. When the capacitors are fully charged, there is no current drawn from the source because they're fully charged. So that means there is no voltage drop across the resistors, because the voltage is dropped across a resistor only if there is a current flowing through it. Now that there is no current flowing through it, there is no voltage across R1, R2, and R3. There are only voltages across C1 and C2. That's important. Okay, so that's how we do it. We're asked to find the energy. Energy of a capacitor can be calculated using 1/2 times the capacitance times the square of the voltage. The first capacitance is what? 10 millifarads. Milli is 10 to the negative 3. And the voltage across it would be 12 volt. And so you get 0.72 joules. What is the potential energy of the second capacitor? Same formula. What is the voltage across the second capacitor? 1/2 times the capacitance is 4.7 millifarad. And the voltage, that's a suspense. What's the voltage? Oh, it's 12. Why? Because it's connected in parallel. We know that voltages in parallel are equal. Okay, that's why the voltages across C1 and C2 are both 12 volt, and you get the potential energy of each capacitor. This is a mathematically easy problem once you understand the physics behind it. Again, when it says it's been closed for a long time, there's no current, and that's why there is no energy, no voltage drop across the resistors. That brings us to the last one. Okay, find the resistance that must be placed in parallel with a 60 ohm galvanometer having a 1 milliampere sensitivity to allow it to be used as an ammeter with a 25.0 ampere full scale reading. Include a circuit diagram with your solution. So a galvanometer, it's a very sensitive instrument. Its sensitivity is so high, which means it can only carry a small current. In this case, it can only carry 1 milliampere. But we need to use this to measure up to 25 ampere. Wow! Something that can only carry 1 milliampere. How do you use it to measure up to 25 ampere? Okay, it's simply by protecting it. How do you protect it? By connecting a resistance in parallel to the galvanometer. So, in short, a galvanometer is converted into an ammeter by connecting a real small resistance in parallel with it. All right, here is a circuit coming up. So that's the current. Here's a galvanometer. And then here is the small resistance connected in parallel. Okay, so when you send that current, at this junction, the current splits into two. 1 milliampere goes through the galvanometer, and the remaining current goes through the shunt. It's actually called the shunt. But we know that the voltage across AB can be written in two ways. It's either this current into this resistance or the remaining current into this resistance. Why? Because we know the voltages in parallel are equal. So we wrote it in two ways. You can see that 10 to the negative 3 ampere times 60, that's 1 milliampere, okay? 10 to the negative 3 times 60 is equal to, all right, so 25 is coming in because that's how much we want to measure. 25 minus 0.001 goes through this, so times RS. You know that mathematically you could have just put that as 25 times RS. And then calculate, you see that you get a really small resistance, right? That is how you work out this problem. Okay, that brings us to the end of this section of, I think, 10 problems, which is really a combination of RC circuits and Kirchhoff's laws, and also converting a galvanometer into an ammeter. I hope to continue the series of DC circuits because I think students find it a little difficult. But with this video and more to come, with more practice, I am sure you'll get to grips with the ideas that are to be used in direct current circuits to find the currents, the voltages, and the energy. We'll see you on the next video. Be sure to subscribe and to pass this on so others are benefited. Thank you so much.